Hello everyone. So let's welcome to part 2 where we are doing the real dynamic programming, because as you have seen on the previous video below the fig tree, that the recursive solution actually took quite a lot of time, even half a second for just changing up $2,000 with the pieces, and for changing up $5,000 you need to wait like nearly half a minute. So basically I just moved to this new location out of the wine garden here to the side of the fields. I'm still using the PinePhone. Watch the previous video if you haven't watched it yet. And we are doing the coin exchange program with dynamic programming now. So let's get started. So what was the previous solution? You know, the previous solution, we basically exchanged the coins, like $2,000, with these 1, 5, 10, 20, 50, $100 coins, or let's just say them coins, even though some of them are paper. And after that, we are calculating how many ways to exchange that. Not really the exchanges, but how many ways it is possible. So we can maybe do this faster, in a faster algorithm, because here we basically just pick the biggest value, imagined how many ways we can exchange it with just 100, 1, 2, 3 times, like $100 used, $200 used, $300 used, etc. And recursively for all of those cases, we recurse downwards and calculated how many ways we can use the smaller coins. That gives us maybe like a n square or n to the third algorithm. However, there are a lot of calculations that we are doing twice, 3 times, so many times, and we are redoing those calculations even though we have once calculated those. And this is one of the 3 signs that shows and tells you that you should maybe try thinking about dynamic programming. Because if you are calculating things that are basically, you have already calculated them, that's a very clear sign. You should somehow cache them. So caching is about dynamic programming. The second is basically if you can bring the problem space into some kind of table. Imagine some kind of table, and it can be one-dimensional, 2-dimensional, 3-dimensional, whatever dimensional, but it always has like a front line. That's how to remember what dynamic programming is. It's like a dynamic system when there is a state. Just now thinking about the 2D, there is like a halfly made grid, and you always calculate the new row of the grid from the previous lines. Maybe 2 previous lines, maybe just 1 previous line. It doesn't count. Anyways, so that's the second. And what's the third? The third is that it's just too slow for the recursive solution. If you see all of these 3, you can think about dynamic programming. So how we are making a grid here, or like basically a grid, just a 2D. Simplify this, and let's say that the coins are like not this. Like let's make fewer coins. Let's just make like there is a coin like $1, there is like a coin for $2, there is for like let's say $4, and there is like let's say $7. And that's all. And there, let's say we only have these values, just for simplicity. And also for simplicity, imagine that the money is just like $10 to exchange with these. Okay? That makes the problem much simpler. So basically, we now have $10 to exchange with only these 4 kind of pieces. And you already see that the $7 you can only use once or 0 times, but maybe we will approach the problem from a different direction also, from going from the lower coins to the bigger ones, unlike the previous recursive solution. So what we can do is that we can think how many ways we can solve this problem if we only use the first coin, like the coin 1. Okay, let's make like a big comment here. Don't find the stars, just like this. Okay, so let's say we only use the first coin. The first coin, if you only use that one, we should call it C1, like coin one, $1 coin. There's only one way to exchange $1, $2, $3, $4, $5, $7, $6, $8, $9, $10. So for all kinds of dollars from 1 to 10, there is only one way to do the exchange, because it will take only the same pieces. Like there is only one way, because there is only the $1 that we can use. So every exchange will be only having the $1 coins, no other coins. That's the simplest case. What about if we are giving the $2 coins to the equation? Can we calculate this line from this line? If there is only $1 to exchange, so let's give one more thing. This is like 1, 2, 3, 4, 5, 6, 7, 8, no, 5, got, no, left out, 9, 10. So if we only have the $1 to exchange, that we can only use the $1 coin for. So there is only one solution. For the $2 to exchange, we can use the $1 and $2 to calculate this. So basically we have a solution of 2. For the $3 to exchange, we can use the 3 times the $1 or the $2 and $1. So that's also 2. For the $4 to exchange, we can use 4 times the $1, or we can use like 4 times the $1 or 2 times the $2. So that sounds like there's two. No, there's also 3 solutions, because basically you can also use the $3, the $2 once and the $1 twice. So that's like 3 solutions. And for $5, you also have 3 solutions, yes, and so on. So just imagine how we can calculate these out of the previous ones. What we can do on the $6, there is like one jump again, as you can see, because the $2 we can also again use. And the 7th we cannot use new, because we can still not use. Wait a minute. How many ways are there for the 7? Because we can use the $7 piece, that's 1. We can use the full $1 pieces, that's 2. We can use the $2 piece with the. We cannot use that with the $7 piece. So we can use the $1 piece and $2 piece for getting a solution. Yeah, it's 4. It's actually 4. And only at the 8 we can do actually the 5 ways. You will see why. I'm already kind of seeing how the dynamic programming will go. I'm starting to see that. I imagine this way. Let's see if this is how it will be. Because what the values are, now I realize, okay, now this is how you can kind of get the hang of it for dynamic programming, is that now you're realizing that how these are calculated. And these are calculated basically by this value is just calculated from the above one. This value, that the 2, is calculated from the, I think, the above one and the before that. Because the 1 coin and the 2 coin itself, that's yeah. And so on. how can I explain this properly in this nice nature at least before the sun is setting. Maybe it will be not done before the sun is setting, but it's still nice time in the nature. Okay, I don't know why I am writing this in the coin sim instead of the TP, but whatever. We can actually, okay, we can actually go this way and delete everything. Okay, anyways. Just remove this. But not from the dynamic programming version. So from the dynamic programming version, we have this solution. And how we are implementing this count? I think what should we do? Is that this will be not recursive, so we don't need the index. We just need the remaining, which is basically we can rename it to money. And then we should make the table. We should make this table. And I feel like instead of a two-dimensional dynamic programming table, we can do like a one-dimensional. Actually, yes. So what we can do is that we can do a stud vector or std vector, as I like to say it, of int table. If we just fill it with ones, but it should be having the size of coins dot size. But it should have the size of the coins, and we should fill it with ones. That's what I'm doing here, basically. Yeah. That's what we are doing. And the thing is that, okay, what we should do here? We should have a loop not from 0 but upwards from 1, because the zeroth case, the zeroth coin, we already handled by pre-initializing this vector. But we should have the loop from 1. Let's do that. Let's get rid of this red. We will just, I don't know, we will just Hallo? Hallo. Nem.
Jössz. Nincs arra senki?
Nincs.
Nem emberevő
Jó. Majd még leszek itt egy darabig, de csak később.
Ja, nem.
Jó van. There are people looking at going with dogs here. Nice weather. So this just gives to the live nature of the video, I think. Okay. So we will find out what to return, and this will not go, and we will go from 1 to size. And just by 1 by 1. So this will be a shift here. Let's just delete this. Let's press Y. Something very big voice is coming from down there. Ooh, the sun is setting right now. Anyways, So we are just going through the coins, and what we will do is that okay, let's get the coin. Coins y, and from here let's think about what we are doing with this coin. We should increment the one exactly from left of us, because there is one more way to do that solution. So we should just pass coins, coin minus 1. Coin is like the current coin. No, this is bullshit. We should do the table. not change the real coins. Oh, sorry. It's so easy to get complicated. There are people flying around. It's just awesome. Maybe you will see them. Maybe not. Parakeeters. So, and what we can do is that we can have like a inner loop. Maybe if you don't see the animals. J. This is going from the chosen coin until the J is smaller than also coin's size. No, it's this for the top, for the table. Okay? So what we are doing now is that we will use the values from the previous line actually. So we kind of need a double buffering. So we need to store the previous line and calculate the new one, and store the previous line and calculate the new one. Or should be actually, because we will be only touching values to the left of us. So it doesn't look like really that we should do that. That's kind of cool. Yeah, we actually doesn't need double buffering either, not just. So this will be like just a line and always update itself. That's a further optimization that I will be doing it, because if this gets online, why not do the more proper solution? I was first thinking about really the 2 degree and calculating each line from the previous one, which would be the vector of vectors. But this looks like better, in my opinion. So yeah. I think that's how I did it for past time. I will just silently do the code like that or something. Sziasztok! I think this is how it should be. Like where we are stepping one by one. So we are not jumping, okay, in the table. We are just stepping. If you go up here, what we are doing is that this is the table, like this. Just one line of it. We are not doing it two dimensional. And what we are doing is that when we are here, we just don't increment it because there is nothing before it. When we are here, we can increment it by by the newly found things, and so on, because we are introducing this second coin in this case. And I'm thinking, what is the solution? The solution will be just in the end of this table. I think that's it. So let's say that what we return, it's the table that size minus 1. And I think that's the solution, honestly. I think that's it. So there is no recursion, and there is two loops, and one of the loops is going from the coins dot size, and the other is going like on the table, which is like basically related to the size of the input, the manipulation. So this is basically big O that. It's linear to that. Because these coins are, of course, this loop is like only 4 times, so that's like a 4 times multiplier. So the whole thing gets linear. And let's see if this works. Let's see. Let's do this. So instead of going sync, do going BP. And going BP here. Okay. Index is not declared, remaining. Oh, of course. Well, what the hell? I don't understand this now. What is index? Aha. Of course, I didn't delete this shit. I hope this is like, no, the table should be like that. Okay. Okay. Of course, I have too many arguments because we should only have the money. At least it compiles. That doesn't sound right. It really doesn't sound right. Good, to be honest. It should be like 10 or something. It's like more than that. So something got wrong. It's a bit cold. And there are light on here. And the sun is setting, but we will somehow solve this. Okay, let's do it this way, that we bring back the original problem. That's surely not good. Okay. So we have that table with the coin size. We have it with the money and one. We should have it with the money. Oh, fucker asshole. This should be like money. I actually explained it, that it will be big O money. The funny thing is that I explained while I'm talking about the runtimes, but I didn't code it that way. So that's it. Let's see what is going now. That still doesn't look good. I'm sure that's not good. So we have money and everything is filled with ones. We are going through from I plus 1, coin size plus I. We are getting all the coin. We are getting giving the coin -1 some little bit, and we are going the J loop from coin smaller than table size, and was J. That sounds good. And the table J plus equals table J minus coin. Oh, it should be good. And table it just returned. So something I look it again, because I just want to increment the table. So what we are doing is that we initialize every value of it to 1, and we are just looking back, and the values that we have previously calculated we can reuse in the new. I might do a Hungarian explanation video of why, but it's basically what we are doing is that the table position J minus coin is basically how many ways to use all possible coins up until those values inclusively for the exchange. So we already have like a already calculated value there, and we just need to add that to okay. Yeah, it doesn't equal, it's like classic. I actually pushed that, but yeah, it didn't go through the latency of the SSH and everything. Let's hope this is like giving us the solution. Oh, and this is the same value. Look up the previous video of mine. This is the same value as in the other recursive solution. So I really think that both of them are right now. And yeah. Once I have made this code in the summer actually as a code kata, so I kind of remember what the value will be, and maybe the best part is that the explanation can be a bit more clumsy because I know what I'm doing, and it just comes up naturally. But the thing is that if you sometimes are in this dynamic programming mindset, you can think out these solutions. And for me, what's harder is that if I am, let's say I would be doing this video next year without doing any kind of dynamic programming like now I did in the summer a bit. If I would do this next year, I would completely get stuck for like an hour. Now that I did it like not so long ago, just some months ago, a similar problem, it kind of comes naturally. So maybe the explanation is not the best. I will try to make it better for the Hungarian version, but you can see that it works faster, and let's just time it. And just for mention, it's now, look how much faster it is. the coin BP than the coin SIM. The SIM, oh, it's actually very fast now, the SIM. It can take like 0.3 seconds. It used to take like 0.5. Now it's 0.3, and the dynamic programming is like 100 times faster. 100 times faster. Not 100%, it's 100 times faster.